happy to be recorded?
No, I think he's happy.
Oh, okay.
I think Michael's happy. Yes, he's happy. Hand up, happy.
Right. Thanks, Michael.
Okay.
I'm going to mute myself and let you go, Scott.
Okay. Just can you start recording, Linda, please?
Done.
Yes. I'll just quickly introduce myself. I'm the CEO of Apera. We've got offices Brisbane, Sydney, Melbourne, Perth. We've been in our 21st year now, so it's we've been around for quite some time, and we've grown into many different areas. Today we're going to be talking about VHP technology with our supplier Amira from Italy. Now, some of you might have seen Pietro speak at the ISP events earlier this year in Melbourne and Brisbane, so you'll know that he has got a great deal of knowledge with this technology. Some of the other things that Apera does, we're an ANATA accredited lab for controlled environments, but we're also healthy building scientists. So we do asbestos audits, hazardous material, chemical hazard managements, neighbours, indoor air quality, mould, all that sort of stuff. And we're very strong in the equipment space. So airflow mapping equipment, particle counters, biological safety cabinets, and we sell, supply and service all of that equipment. But today we're here with our good friend Pietro, who's got a fantastic depth of knowledge in this industry globally. We're happy to be running this webinar today. So I might hand over to you. Now, Pietro, and you can introduce yourself and Amira.
Thank you, Scott. I'm the product and export manager of this company, Amira, and we are a relatively small company, Italian, 100% owned by my boss. And our company in the last 10 years developed and put on the market a VHP generator to perform biodecontamination of different applications. One of the main market where we sell is pharmaceutical, especially in the aseptic field. And today I would like to give a sort of overview and introduction about what are the benefits of this technology and how this can help you in your processes, and especially giving some tips on when, just in case you may be interested, what are the things you have to keep an eye on, okay, to keep under control when you decide to go for a biodecontamination system. So I will now share a presentation. Here we are. Okay, Linda just confirmed that we can see my presentation. So correct?
Yep.
Okay, great.
Yes, correct. Pietro.
Okay, so this is.
Sorry, we can see.
Yeah, great. So this is the company name, as mentioned, Amira. And we would start with a very good question. That is, what is biodecontamination? I would like to give you some tips and advice exactly on this topic, biodecontamination. So it's good to put some common bases, in understanding what the meaning of this word is. And to do that, I will start from the latest regulation, especially in aseptic pharmaceutical field. That is the Annex 1 to the GMP. Annex 1 to the GMP regulates the aseptic production in Europe, but it's a regulation that is worldwide recognized to be the gold standard for aseptic production. So in the glossary at the end of the big Annex 1, at the end in the glossary, you may find some specification, some explanation of the terminology used in the regulation. And I just really easily copy-paste the definition of biodecontamination. And the definition is pretty straightforward. It's a process that eliminates viable bioburden via using a sporicidal chemical agent. Just to be double sure of a common understanding, I also copy pasted the bioburden definition. That is number of microorganisms associated with a specific surface, for example, or environment. So you immediately see that biodecontamination is a process that you, in reality, in an aseptic pharma, it's used every day because every day some biodecontamination is required, some killing of bioburden via sporicidal agent. It's already performed. But somehow this is not enough to understand what biodecontamination is for the aseptic production, because the process that eliminates viable bioburden, no one defined exactly how big is this viable bioburden at the beginning, how small it should be at the end. So it's a process that if we take the root of the word, that comes from bios and decontamino, so from Latin and Greek, means to take out any life form. So this biodecontamination process immediately seems to be more similar to a sterilization process. So to really get rid of any possible contamination from a microbiological perspective. And in fact, in the 4.21 in that specific chapter of the new Annex 1, it's clearly mentioned the sterilization as a possible alternative to the sterilization process. In that specific case, the Annex is speaking about RABs, so the restricted area barrier, where actually the aseptic production is manufactured, so where the sterile medicine are filled up. And it's talking specifically about the gloves that are installed inside that specific area. And the regulation rise that requirement. The gloves should be sterilized or effectively biodecontaminated by a validated method. So again, this fulfill somehow the explanation of what really biodecontamination is. The biodecontamination is a process that use a chemical sporicidal. So it's not a process that use thermal or gamma radiation or any other kind of technology to reduce the bioburden, but by the contamination you use specifically a sporicidal agent, so a chemical compound, and it's also capable of achieving a completely killing of any possible microbiological contamination of your surface. In that case, it's a glove, but that works for all the regulation basically. In all the Annex 1 define the biodecontamination in that way. And now here we start to see the benefit of using a biodecontamination process together with the sterilization processes that already exist in a pharmaceutical company. So already today, autoclaves are used to get sterilization of many items, and gamma radiation is already used, for example, for garments that comes into the class B for the dressing. But there are many different places in an aseptic production, or many different things that cannot be sterilized by any other method, like thermal or gamma radiation. So this is where adding a biodecontamination process to the existing process may be really beneficial. So to give you some idea of advantages of using biodecontamination, I would start with our specific experience. This short video I will show you was done in our clean room. I'm now in that specific moment in our company, Amira Tech, which is a space where we have a conference room, the one where I'm standing now, but we also have a laboratory equipped with different isolators and tools to make a study on VHP. And we also have behind the door that I have behind my shoulder, we have a clean room, a Class B clean room, where we make tests, we perform video, we do training. So my idea is also to show you some video created exactly inside that space to help you understanding the benefit of using an H2O2 hydrogen peroxide VHP vapor technology. And one of the concrete advantage are mentioned right there. So it's easy to use. H2O2, it's very, very easy to use, and you will see in a minute. Safe for operator environment, because H2O2 by nature is oxygen and water, so will just break down into those basic components. Leaves no residues, but we will see that maybe later a little bit better, but especially can reduce any bioburden contamination to zero. So now you see me entering in our clean room and in bringing our VHP generator inside, just to show you how easy it is. And that's pretty old. You take the VHP generator, you bring into the room, you take out a power plug, you connect to the building, and you start decontamination. We will see an actual decontamination in the next video. With that simple operation, you can get a surface sterilization, where, for example, in that room where another kind of sterilization is actually not possible, because you cannot put the room under into an autoclave. But the H2O2 and the vapor from H2O2 can get the killing, can get the sterilization, can get the ground zero on your microbiological contamination, can get the bio-decontamination done into your specific application. So maybe beneficial to understand what are the typical application for a bio-decontamination solution, like VHP. Most commonly, the typical application are transfer chamber. I think the real that's a real, I would say, pretty new application. Not really new, maybe started 5 to 10 years ago as a real application, but it's now becoming more and more important due to also to the Annex 1 and other regulations. So transfer chamber are double door equipment, double door solution, like an autoclave, that helps you transfer a good from a non-classified area or a less classified area into a classified area, like a Class B. And this is a pretty big one. I just took that picture because that's one of our installations, so it's nice to see. But the idea is you put a trolley full of your stuff inside that chamber. You treat the goods with VHP, with H2O2 vapor. You get the sterilization of the surfaces done with the H2O2, and then you pass it to the next step into the classified area. One of the oldest and probably 99% of the application worldwide since 5 years ago was only that one. It's isolator for sterile production, or isolator for sterility test. It's even mentioned in several places in the Annex 1 and from FDA as well, that any any isolator must has a biodecontamination process on board by definition, and VHP is 100% the most common technique to make a proper sterilization of surfaces of the inside of the isolator with a spray agent. The very last, but becoming probably the first application since the last 5 years, it's room. Mainly when wraps or filling line machine, open filling line machine are present into the clean room, that's becoming a critical part of the process for any aseptic production to have a biodecontamination program of the whole clean room together with the filling line machine inside. And that makes a lot of sense. I mean, I transfer good doing a proper biodecontamination. I have isolators in a sterility area that does a proper biodecontamination for sterility test. And then what about my clean room where I actually fill up the product? So that's also very important application. Those at least are the typical application in pharma. One thing that I would like to discuss now is we mentioned H2O2 mainly because we produce VHP decontamination systems, but also because it's definitely 100% worldwide recognized to be the proper molecular to perform biodecontamination, and definitely the most common, 100% the most common worldwide everywhere. So it is very, very critical and important to make a distinction because H2O2 is a little bit tricky. It's similar to water. So exactly like water, you can have a liquid H2O2 in a glass or in a bottle, okay? And you may have, exactly like water, a gas phase H2O2. Like for water, it's relative humidity. The relative humidity in the air that surrounds you, it's a gas version of water, okay? So H2O2 historically divided into two different approaches, I would say technologies, by manufacturing people who manufacture systems that works with a vapor technology, and people that manufacture a system that works in an aerosol technology. So the aerosol technology and the vapor technology are different, and it's becoming really critical, and it is an important tip whenever you want to invest in a biodecontamination system to distinguish between those two technology, or technique maybe is better than technology. I should change the word maybe. Anyway, so first, to again common understanding, I like to put everyone on the same line, starting from definitions. So we start from the definition from the book. If you go on a physics book, in vapor, it's a gas, okay, that can come back to liquid. So gas can be condensed to liquid, okay, at the room temperature, basically. So again, thing to water, super easy. You have your room full of gas water, relative humidity. If you push your relative humidity up to 100% relative humidity, then you are increasing the pressure of the relative humidity, and magically you have rain. So 100% relative humidity means condensation of water, means that the gas phase come back to liquid. You didn't change the temperature, you just changed the pressure. So this is the definition of a vapor, but still it's a gas. While aerosol is not a gas, as a suspension of teeny small liquid droplets. Okay, the definition from the books says particles, but I would mention droplets because it's a liquid. Okay, so droplets is more appropriate as a name. So you have to think about it when you speak about decontamination, when you think about the idea that you want to perform biodecontamination of a complex thing like an isolator, like a room. Having an aerosol or having a gas makes an extreme difference into many different extreme, let's say, difference into several, several small details that are very important. So to show you physically this, again, I made a simple experiment by gassing my clean room. So, just want to show you, this is, not sure if you can see 100% clear, but this is an sensor that measure the ppm, the concentration of H2O2 in my room, and it's actually around 180 ppm. So to show you that we do have a high concentration of H2O2, I'm actually gassing now. The room is full of H2O2 gas. And if you see the video, we'll now move the camera out, showing our equipment, showing you in the room. This is a distribution fan. This is our VHP machine. I mean, there's no trick made out of the video. This is just a simple camera, like the one that is showing you my non-beautiful face. And you can clearly see everything because it's a gas. When you walk into your room and when you wake up in the morning and you go for breakfast, you see everything with your eyes clearly and easily because you are submerged by the gas version of water. Okay. Now, what happens if I start? Come on. What happens if I start an aerosol system? That it is exactly what happens when you start an aerosol system. It's a fog of droplets. So everything start to be wet, and at a certain point you don't see anything. Bye-bye. Visibility to zero. That is because you are generating droplets of liquid, and the droplets of the liquid goes everywhere and settle down and are big, and they wet everything at the end of the process. And your camera is wet as well at the end. So this visual experiment, I think it's very, very helping to get the reason why that we will also rediscuss in a minute. There was a big change from the draft to the definitive version of the Annex 1. Precisely, in the draft version of the Annex 1, looking to the chapter speaking about the isolator biodecontamination, there was 3 techniques mentioned. One was the gas phase sporicidal, one was the aerosol phase sporicidal, and one was the vapor phase sporicidal. Okay, the distinction between gas and vapor, it's maybe not fair as they did, but anyway, there is a distinction because the gas cannot condense at a room temperature, while the vapor, yes, but still they are gas. In the definitive version, the regulation committee decided to remove the aerosol from the equation. So that's an important signal from my perspective, at least, that also the big expert writing the regulation recognized the aerosol as not very good, at least for the isolator, sterilization, biodecontamination for aseptic pharma, because it's an aerosol, because of the technique. And to better explain that specific fact, I also added these small table that summarize advantages and disadvantages, but mainly let's say differences from the two technique. First, and also this wants to help you save this table. I think helps you to understand whenever you speak with a potential supplier exactly where they position it with the technique. Then you're free to decide whatever you want. I mean, it's your choice, but at least you know who you're talking with, because sometimes it's still very confusing. Supplier just say, hey, I'm an H2O2 biodecontamination system. Okay, but are you in gas or in aerosol? Oh, I have maybe an atomized, micronized, dry fog system, Micheller system. There are many fancy names, and you can get confused on what exactly you're going to buy. So the easy way to distinguish between the H2O2 decontamination in a gas phase and H2O2 decontamination in aerosol phase, it's looking with consumables. Consumables, so the H2O2 liquid that you start with for your process, it's most commonly 35% when you speak about the vapor, most commonly 3 to 10% when you speak about the aerosol. So why the aerosol use a much lower concentration than the vapor generator? It's easy to explain because H2O2 is corrosive and it's a liquid. Yes, so in a liquid phase, H2O2, it's corrosive. And that's easy to understand. You take your iPhone, or your computer, you take a piece of iron, okay, an iron nail in your hands. These can stand surrounded by water in gas phase, okay, the humidity for all its life, no problem. But as soon as you put some droplets of liquid water on top of your device or your iron nail, then you get the damage. So it's a liquid which causes corrosion. So the aerosol must keep always a very low concentration of H2O2s sprayed into the room, because that will corrode your clean room, while the gas, the VHP, the vapor systems, can go with a much higher concentration because it's a gas. So there will be no issue with compatibility with material. So that's the tricky. I want to put on the table very easy to understand. If you're talking with an aerosol supplier or a VHP supplier, just ask, okay, what about the consumables? What is the concentration of the H2O2 you use for your machine? And if they're straight to 10, I would say it's most 90%, 99%, it's an aerosol technique, while it's at 35%, it's most probably a VHP. So just to stay focused on the specific difficulties or advantages, disadvantages, the main three I would mention is diffusion. I mean, there is no discussion. If I need a proper assurance to get every point of my filling line machine decontaminated, if I want to get the killing, the reducing of the bioburden everywhere, in every single spot of my room, then the gas will be the perfect choice. Any aerosol, even the most advanced, will always be depending on how big is the droplet, how big is the speed of your droplets. If you have any obstacle, it will impact the droplets and stop the droplets. So gas will always be the best choice. The second point is there will be no residues after the cycle. Gas leaves no residues by definition. It's a gas, okay? While whenever you spray something, I show you in the video, everything gets wet. And when the liquid dries out again, there will be questioning. Oh, okay, I wet my surface and then I have a dry out phase. So what about the residues? There are residues, there are no residues. At least it's a discussion point. Last but not least, H2O2 in a gas phase can penetrate the HEPA filters. I mean, HEPA stops everything bigger than 0.3 nanometer. So the gas can, 0.3 microns, while the gas is less than 0.3 nanometer. So the gas can penetrate the HEPA filter, while the droplets cannot, because droplets are always bigger than 0.3 microns. It's usually around 5 to 10 microns dimension, I would say. So for all those reasons, or at least this is my idea, for all those reasons, and for the fact that the aerosol may be very difficult to validate up to the killing point in the distribution and reproducibility that are needed in pharma, the regulation body decided to take it out from the approved method for decontamination of an isolate. So we discussed about validation, or we told that an aerosol may be difficult to validate. So it's fair now to spend some word on what validation means when you're talking about a biodecontamination equipment. Of course, everything should be properly validated, defined, and controlled. Of course, it depends on the different application. The Annex one push a lot of attention of validating. There is also a nice chapter explaining the effectiveness of any fumigation agent. The dispersion, okay, should be understood and validated. Speaking about a VHP into clean rooms. Again, speaking about the isolator, sporicidal agent in a gas or vaporized form, as mentioned before, but it must be controlled, it must be validated, and so on. For RABs, again, robustly, you have to demonstrate and validate all surfaces, must be properly addressed, and you must create an environment suitable for aseptic production. So what is validation is? Basically, you are testing and validating a killing agent. Biodecontamination is about killing microbes. So you need a biological indicator. Biological indicators are, in the case of H2O2, are usually metal disc, but they're different format. But I would say most commonly metal disc with a suspension dried, okay, on the surface of your metal disc, made out from Geobacillus steatorhaemophilus. So why these? It's widely accepted to be the worst case. It's been demonstrated also by several publications that the Geobacillus steatorhaemophilus is the worst case against H2O2. So you want to be sure about the killing, so you must use the worst possible microorganism. And it should be a prepared biological indicator. This of course available on the market. I will show you in a minute through a video. So these biological indicators should be charged, that should be loaded with 10 to the 6, 1 million spores of these bacteria, because you want to prove again the bioburden reduction to zero, ground zero. You cannot leave anything behind. So you need a proper log reduction. That is the log reduction of the sterilization, 6 log. Okay. Now with this simple video game made within our clean room, I just want to show you those are available on the market, biological indicator and chemical indicators. The chemical indicator is mainly meant to show you, help you understanding the process, the distribution of your agent, and so on. But the real challenge is the biological indicator. And when you prepare a room or an isolator or anything you want to validate, you take the biological indicator charged with Thermophilus, and you need to, enumerate every single biological and chemical, and those needs to be positioned on a map. So in that case, that is my clean room, and you see every single black dot. It's a position of biological indicator, including the ceiling, including the floor, including the changing rooms, including the laminar flow, if any, including all the corner, different height, and so on. So that is the challenge you need to win to demonstrate your bio-decontamination equipment really properly works. The biological indicators and the chemical indicators needs to be positioned in that way so that all the surface is exposed. And again, one is a quantitative information, give you the killing ratio, 6 log. The other one is more a qualitative information, gives you the idea if really the H2O2 was there or the biological indicator just died by case, okay, which is not easy, but it happens. And this needs to be positioned everywhere properly. Again, that's me positioning biological indicator. Oh, I didn't remove the audio. You see different height, for example, in that corner. In the other corner, you see another biological indicator there. You see another biological indicator there. So different places in the room. And of course, if you have a filling machine, if you have a wraps also inside there. That is very, very, very important point, is where do you position those biological indicator? How do you position it? It's important. I show it you, okay, different height, different places, should be completely exposed. You choose maybe also the right biological indicator, fantastic. But then especially the new Annex one, but that's an old way in pharma. Everything must come through a proper risk analysis. Also, the positioning of the BIs should follow a proper risk analysis. So I would say that that's the other really important part of what I want to tell you today, other than the advantages of the bio-decontamination, the different technique, and also a trustable partner. It's easy to invest a lot in a nice bio-decontamination system, have it installed in your facility, and then not be able to use it because the validation, it's a poor validation. The bio-decontamination system is not only buying a machine, is to validating a machine into your specific application. That may be an isolator, maybe a pass box, maybe a room, maybe a wraps, whatever it is. The validation is a critical, important part of the package you buy from your supplier. And the risk analysis is part of that validation, and the ability of positioning the BIs in the proper place, aseptic, the most important places, the dirtiest area, the most difficult to reach areas, but not only, okay, all the building, all what was behind, what is behind this validation, it's important. It's one of the things that assure you to invest your money properly in a real good solution that helps you with bringing advantage on your process. So it's not only, again, to buy a machine, it's also to validate that machine with a proper biological indicator in the proper position into your proper application, keeping in mind that sometimes are also many biologicals in many positions with many runs, and this may be tricky if the supplier of the technology is not prepared to support you properly. So that's some very important things. Before to start with the question and answer, I always like to leave some time for questions. I just would like to mention something about our company, just very briefly. As I mentioned before, we have been done these job of building and distributing worldwide VHP generator for the last 10 years, and we have now total overall installation of more than 500 machines in 36 countries, including Australia. And in most of those countries, we installed and validated our machine in many different markets, many different applications, starting from pharma, which is our main background, aseptic production, microbiological laboratory, but also going to research on animals, also going to university, also going to food and beverage, and moving to hospitals, biosafety laboratory, a lot, level 3, level 4 worldwide. So we have a wide experience in that technology, and we also have different solutions that feeds different needs. So just feel free maybe to come back to Amira and start a discussion if you need any further information of this solution for your needs. Right time for question and answer. Scott, what do you think?
Yeah, Pietro, thanks very much for that. Yeah, I think one of the things that attracted me to Amira was we weren't, because we're an end user of decontamination technology and have tried a number of various systems over the last 20 years. And yeah, I'm not a fan of being locked into a chemical supply, which is what's happened to us in the past, and we've paid through the nose for it. So with the actual VHP solution with Amira, yeah, you can buy it from probably somebody that you already have on your books, which I think is a really big advantage. And then it's just a matter of coming up with a recipe and validating it for your purpose. Now, just a couple of questions.
Sorry,
and this is
sorry, yeah, I was going to ask, are you going to read out the questions, Scott? I'll let you do that then.
Yes. Okay. So this is a really interesting one from Damien. He's talking about VHP as sanitation and not sterilisation and the requirements. Hang on, just someone moved it.
Yeah, let me open the question because it's important.
Yeah, if you open them, Pietro, you'll be able to see. The first thing he said was, does it not stipulate a log 6 reduction?
Ooh, sorry, that's my lack in English. What stipulate means?
Does it not say or specify a log 6 reduction?
Okay. In the regulation does not, it's tricky because the point is never specific. The log reduction is not really specified anywhere. Even for sterilization. If you look in the Annex 1 and go to sterilization definition, what is the expected level of sterilization? No one speaks about 6 log reduction. That's calm. 6 log comes from a much more complex idea, which is the SIL, the sterility assurance level. Damian, that would be a pleasure for me to maybe discuss about that, but it's a very long discussion because we need to come back with what a sterility assurance level is, probability of failing a specific decontamination process or sterilization process, and that's becoming long. But just as a short answer to your question, if you ever tried to purchase an isolator, either for sterility test or for septic production, if not, ask to anyone who has an isolator. Any isolator in the world is validated with 6 log reduction on Stereothermophilus with VHP. No discussion. Apart from the regulation, that is the state of the art. And then the regulation also requires you, but the answer is pretty complex. So I will discuss with you personally, maybe in another session.
Yeah, we might get Scott and you to have a connection with that. The other thing was he said VHP is sanitization and not sterilization.
Yeah,
and
yeah,
the
yeah,
requirements
correct.
are different and distinct.
Yeah. Thank you again, Damien. That's relatively correct. In that sense, the difference between VHP and sterilization is not even correct to say it that way. VHP also can be a sterilization process in certain condition. So the difference between a bio-decontamination process and a sterilization process, so we get away from VHP for a moment. The difference between sterilization and bio-decontamination is that the sterilization requires the ability of penetrating the material. So temperature, yeah, I can get inside my packages. Gamma radiation, I can get inside my packages. Ethylene oxide, which is a sterilization method, can get inside my packages because I go under deep vacuum, suck all the air out. Okay, I have a big autoclave, basically suck the air out, deep vacuum, injection of the gas, ethylene oxide, and then the ethylene oxide can penetrate the package. So that's the sterilization. Biodecontamination, that's not required. Biodecontamination is a surface sterilization. So call it surface, I don't know how you want to call it, but the idea is it's different from sterilization, not because you achieve a different result. You still can get the same 6 log reduction on the same biological indicator, exactly like an autoclave. The difference, you cannot penetrate the material because you don't have the vacuum situation. And nowadays, there are many companies substituting the old-fashioned ethylene oxide sterilization equipment with a VHP sterilization equipment. That is a chamber that goes under deep vacuum and then inject the VHP. So I hope I answered properly your question, but yes, VHP can be a sterilization method if you apply vacuum. That's impossible in a room or an isolator, so it remains not a sanitization, but a bio-decontamination. This is how the Annex 1 defined the VHP, not as a sanitization, but as a bio-decontamination, which this is why I'm trying also to make a clarification what this terminology means, right?
Perfect. Thank you, Pietro. I think Damien had to go, so maybe we'll connect you and Scott and Damien to sort of go through that and have a little bit more detail.
Please.
There is a couple of other questions. Scott, do you want to do them or?
Yeah. Let's do it. If we have time, I mean, I would like to answer.
Yeah. Okay. So presumably the H2O2 will break down into H2O. What happens to the residual water droplets or vapor around the clean room?
Okay, that's correct. The H2O will break down to water and oxygen, but at more time than you expect. So the aeration will not be done by waiting for the molecule to break down. It takes 48 hours. It's not feasible. You cannot wait 48 hours before to enter your room or your isolator to start the production. So the usually the aeration is done by introducing fresh air, switching on the ventilation system of your room, starting the ventilation system of the isolator or the passbox, so you remove the gas from the application. And then when it goes to the atmosphere, then it breaks down in 48 hours to oxygen and water. So from that perspective, it's an environmental safe technology, so environmental friendly safe technology. There are no water droplets, not with a VHP. With a gas, forget the water droplets. It happens only with the aerosol. And in case of aerosol, then you have water droplets everywhere, and then you have to wait for those to dries out. How many ppm the concentration? Okay. Last question is, how many ppm of the concentration of H2O is suitable for the contamination phase? That's a fantastic question. I think if I could have €1 for every time I hear that question, hey, I can retire for the rest of my life. Unfortunately, it's a super complex answer. There's no answer in reality. Different school of thinking. I don't have an answer. No one has an answer. I personally have a lot of experience. I did cycle with 50 ppm, and I did cycle with 5,000 ppm. So it works. Both of the situation is not the only parameter you have to keep under control. Not only concentration. My personal golden rule is 200 ppm. It's a good amount of ppm you should expect in the decontamination, but it could be everything accordingly to the different applications. So also that topic is a very interesting topic. Maybe we can set a section also with was the guy Mr. Som.
Yes, you've got lots more questions now, though. They're cracking on.
Let's go on. For clean room decontamination, as VHP can penetrate HEPA, should we need to start a cycle recirculation fans running? Okay, so depending on the application. For example, in isolator, that's very common. In room, don't do it, because the ventilation system of the room will leak. It's not tight. It's not designed to be 100% tight in recirculation, especially in pharma. So it will leak everywhere, and then you have H2O in every place. But potentially, yeah, that is possible. It's just a question of if it is feasible in your specific application or not. And it doesn't really have any benefit, honestly, the recirculation idea. It's mainly for biological contaminated application, biosafety application, where the filter is full of microbes. In that case, it's good because before to change the filter, you can sterilize the filter. Sorry, I go fast because I see a lot. Do you measure the oxygen availability? Ooh, that's interesting question. No, because we are talking about ppm, not percentages. So, different. No, wait. Do you measure the oxygen availability when using different batches of H2O2? Then I don't understand the question. You mean the concentration of H2O2? Maybe, because the oxygen availability is another way to measure the concentration of H2O2, I guess. So usually we trust the certificate of the manufacturer. If the manufacturer tells you it's 35% H2O2 and the stability is 1 year, and I'm within the stability, it doesn't make a sense to check it again, but it can be done pretty easily. The H2O2 stability is I don't remember the English name for this. Titolazione. The titration is a titration method with permanganate, potassium permanganate. So it's something very, very easy to check every day if you want. I've heard that carbon filters can be used to catalyze the H2O2 into H2O. How effective is this? That's wrong, I'm afraid, because yes, carbon filter can suck the H2O2, but it's not a catalyst. It's a sort of a filter. So a carbon filter absorb H2O2 up to the point where it's saturated, and then everything goes through. So it's not a catalyst. A catalyst breaks down the molecule and it's long lasting. It doesn't stop the molecular, just break it down. So carbon filter, be careful, is not a catalyst. It's a sucking technique. It's like a sponge that absorbs the H2O. It works 100%.
That's the word, good. Absorbent. It's an absorbent.
Okay. For until it's full. Is there any stabilizer added to the H2O? Absolutely, yes. Every H2O in the world is stabilized, because otherwise will decay and bye-bye the concentration. Usually the higher volume, the higher concentration is less stabilized. 35% is less stabilized than 6% H2O, usually, because it's more stable. But anyway, apart from that, everything is stabilized. And that's another advantages of using a gas. When you vaporize the H2O, you have physically a vaporizer, so a heater system. And the heating system, every droplet is vaporized. So it's like when you boil water at home, all the salt, all the stabilant stick on your pot. So everything stick on the vaporizer. You only have a perfect, pure, free residues H2O out of your machine. While when you aerosolize H2O, you spray droplets. Those droplets are liquid to liquid. So this contains all the stabilant inside the liquid H2O that you buy. And this will hit the surface, dries out, and the stabilant is in your clean room or in your application at the end. We have also been advised to maintain a temperature 18, 24, and 40-60% in our isolator. Is that normal? Absolutely, yes. Potentially, I would say this is mainly because it's an isolator. You will not produce a medicine at 4 degrees C. Okay, so usually in pharma, every aseptic production is in that range. But it's another reason. Maybe this Andrew Goodman could be a good idea to have a session with you as well, because also it's a long discussion on how the VHP works in the cycle. H2O, it's a gas, but it's a vapor as well. So if you have a very, very cold temperature, let's extreme, I don't know, 4 degrees C. So again, you are in the fridge and you start to generate a vapor. The vapor condenses back immediately to water, right? So it's normal. It's like when we go out and it's freezing and your breath condense into liquid. So and you don't want this, because then you are back into the problem of the aerosol. So of course it should be a reasonable humidity and temperature as a starting point. Okay, last question, Hillary. Okay, yes, you meant exactly the concentration of H2O. What stabilizer is used? Nobody knows. Is one of the big secret of, and that's actually a good hook for what Scott commented before. One of the big secret in producing a stable H2O is what stabilizer you use to keep it stable. There are on the market available H2O. I'm speaking, for example, for my 35% H2O. You can buy it from probably €1 per liter up to €100 per liter. €1 against €100 per liter is not the same H2O, sorry. It's 35%, yes, completely different the way it's stabilized. And this is the big secret, that it's kept from any H2O manufacturer. So this is all the reason why some other supplier, not me, they tend to stick the customer with their personal H2O, because this is their secret. This is where the money are to sell a good H2O. So maybe you have RFID code on your bottle and you are obliged to use only that specific supplier of H2O. In our case, we prefer to leave the customer free to buy a good quality H2O on the market, spending a reasonable amount of money. but no one knows exactly what stabilizer is used apart from the supplier of H2O. You may ask to your supplier maybe. Would it make it difficult to validate the efficacy of the specific brand? No. Look, the efficacy, it's independent from the brand you choose. The 35% H2O is 35% H2O. That, okay, I know the discussion because I sold in pharma in the last 15 years or so. You use IPA, isopropylic alcohol, and in 70-30%. Any isopropylic alcohol is isopropylic alcohol 70-30%. It doesn't matter. Okay, but still, it's a little tricky when you change the supplier. Will really be the same. Is the same story. It's 35%. It doesn't really matter. But if you want to do everything properly, super pharma oriented, no one can complain. At least choose the right supplier from the very beginning, so you don't have to change it anymore. 35% good quality H2O. That's it.
And I think on the top of that too, Hilary, when you take on Amira equipment, part of it is validating it in any case. So at the time you're validating the equipment, the process, as well as the chemical supplier, you come up with your recipe of how you're going to do the room, and that's all done with chemical indicators, which is quick. Then you can, once you're happy that you've got everything working with chemical indicators, then you can move on to biological indicators, because they take a little bit longer to validate, because you obviously got to incubate. So it's part of that, that process, really.
Okay, well, I think that's we're at the end of the questions, and a few people have had to drop off, but thanks everyone for joining us. Scott, Pietro, anything else you want to say? I mean, we'll touch base with everybody, hopefully going forward, just for any of the additional stuff. I've made a note of Damien and Andrew's details anyway, so thank you everyone for joining us.
Yeah, thanks.
Thanks.
Thanks, Pietro. Thanks, Linda. And Pietro, what time is it there in Italy?
Good morning.
Now it's 4:40 in the morning.
4:40 a.m.
So I just stay in the office,
Have a nice day.
I stay there, I work. And
thanks very much, everybody, for participating, and we'll make this available on our Pira's YouTube channel as well. And we'll